Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today I want to continue with our series on writing a ray tracer in C++ using, as far as possible, only the standard libraries and the SDL2 library so we can display a result in the window. If you remember from the previous episode, we looked at computing ray-sphere intersections and we went on to show how we could create an image of a sphere shaded according to distance from the camera. Now, that's not really ray tracing, although it served its purpose to demonstrate that everything was working as it should, but what I want to look at today is how we can go about implementing basic lighting. Okay, so before we jump into that, I'll just say, as I always do, that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so you don't have to miss any future videos. Thank you very much. Anyway, let's jump to it and let's have a look at how we can compute lighting with our very simple ray tracer. So in the last video, we looked at how we could compute ray-sphere intersections and use that method to create a very simple ray tracer that produced an image of a sphere. To be able to see that the sphere was actually round in 3 dimensions, we then went on to shade it according to the distance of the points on the sphere's surface from the camera. This worked quite well and gave us a nice-ish image, but it isn't really what ray tracing can do. In order to make things a little bit more realistic, we should shade our sphere according to the lighting in the scene. That's what we're going to look at in this video. We will implement the most basic form of shading according to the lighting in the scene, initially for the case where we have just one point light source. In later videos, we will then go on to increase the complexity to handle multiple light sources. So how do we calculate the shading of surfaces according to light sources? Well, actually it turns out that this is quite easy to do, at least for very basic surfaces. We won't be discussing anything here to do with physically based rendering or PBR or anything like that. That is a topic for another set of videos which I might go on to do at a later date. For now we're going to focus on very basic diffuse surfaces. Let's have a look at a very simple example. Here we have a surface, or part of a surface, shown here as the silver patch. This surface has a normal, as indicated by the vector arrow shown in blue, and we have a light source, shown here in white, on the left-hand side of the image. Note that here we are going to assume that our surface patch is very small compared to the distance between it and the light source. This doesn't show in the illustration, but I've had to keep it that way to make it visually clearer. Now we consider a ray between the center point on our surface and the light source, as shown here in red. In reality, we would cast rays from the point on the surface that the ray from our camera has intersected with, but for this purpose, we're going to consider only a single point on the surface. In this case, let's call these two vectors A and B as shown here, with vector A representing the ray from the light source to the surface, and B the normal of the surface. Now, we compute the intensity of the illumination of our surface. All that we need to do is to compute the angle between the vectors A and B. This is easy to do if we remember the equation for the vector dot product that we have seen before and is shown here. In this case, the angle theta is the angle between the two vectors as shown by the yellow curve. We can see that we could easily rearrange this equation to give theta as follows. So, all we need to do to compute the angle is to take the vector dot product of the two vectors and divide that by the product of the norms of the two vectors. Then we can simply take the inverse cosine to get the final angle theta. The intensity of illumination of the surface for this light source is then linearly proportional to this angle. As you can see, as we rotate the surface and normal away from the light source, we get less illumination. And as we go the other way, back towards the light source, we get more illumination, with the maximum occurring when the surface normal is exactly parallel to the ray from the light source. So how does this relate to shading a sphere? Well, as we scan rays out from our camera, they will intersect with different points on the surface of the sphere, and we simply compute the angle between the surface normal at that point and the ray from the light source. It really actually is that simple. If we start with a simple approximation of a sphere, as shown here, you can see how that will work. In this case, the faces that have normals pointing towards the light source are bright, while those with normals pointing away are dark. As we increase the number of faces, we see that this begins to look more and more like a sphere, before eventually we get the smooth surface that we were expecting. Of course, in ray tracing terms, our sphere is not composed of flat surfaces, but if we continue making the faces here smaller and smaller, in the limit that they tend to infinitely small, we will get the shading for a proper sphere with a smooth surface. Notice that as the angle of the normal vector, shown here in blue, varies across the surface of the sphere, so the intensity of the illumination changes, being brightest at this angle, to darkest here, when the normal vector is exactly perpendicular to the ray from the light source. After that, as we continue to increase the angle further, there is no illumination from the light source at all. So, we know that if the angle between our surface normal and the light source is greater than pi by 2, then we will have no illumination, and so we don't need to bother doing anything else. We can use that fact to save us some compute time later on. Right, so that's really it for the basic theory. Let's jump in and have a look at how we can implement this in C++ code. So, as you can see, really the theory is very simple. All we need to do is to calculate the angle between the normal of our surface at a particular point and the vector between that point and the particular light source. Let's jump into the C++ code and have a look at how we can actually implement that practically. Okay, so I've gone ahead and I've copied the code from the previous episode into a new folder or new directory that we're going to be working on. If you've been following along with the series, then you should have this code in one directory or folder already, so you can just carry on with that. If you haven't been following along, then you can either go back to the first episode and work through it from there, or you can get the code up to this point from the GitHub repository. There's a link in the description below, of course. So I'm going to first of all go into the QB Raytrace subdirectory. We don't need to make any changes elsewhere. And here is the code that we have there. And the first work that I want to do for our video today is in scene.cpp and scene.hpp. So initially, we're going to look at the file scene.hpp, and we're going to make some changes to, first of all, the way that we store objects, and then to go on to actually implement light sources, or very simple implementation of light sources. So let's have a look at scene.hpp. So this is the scene.hpp file that we've developed before, and we're not going to make too many changes. The only change I want to make at the moment is to hash include here memory, like so. And we're going to change how we store our objects. So when we wrote this before, we simply created one individual instance of our sphere, which we called m_test sphere, and that was really sufficient for what we were doing at that time. Now that we want to be able to build up towards supporting multiple objects, we're going to have to change the way that this works. So let's just delete that code completely that we had there, and what we're going to do is we're going to define a list of objects in the scene, like so. So that is going to be std vector. Okay, now we're going to use std_shared ptr qbrt : object base. So let's just have a look at what's going on there. What we're doing is essentially creating pointers to instances of our base class for our object. So if you remember back to the last episode, we didn't just create a class for spheres, we created a base class, and then the class for spheres inherited from that. And this is one of the core or principal reasons why we did it that way, is it means we can create a single variable here that can store a list of all of the objects in our scene, regardless of their specific type. As long as they inherit from object base, we can store them in this list, which is very powerful. But we can only do that using pointers, and rather than using raw pointers and the kind of C sort of way of doing things, I've tried to go with more modern C++ syntax, so I'm using the shared PTR from the standard library to do that, which is safer and generally more secure than using raw pointers. And of course we store those in an std vector because we don't know how many there are going to be. That's going to be called m_object list, just like that. So let's save that. So that is everything I want to do right now in scene.hpp. Let's jump into scene.cpp and have a look at what changes we need to make there. Okay, so this is the scene.cpp file. Apologies there, it actually is scene.cpp. And first thing that we need to do is we want to change here so that when we construct our scene with the default constructor, we create our initial test sphere. So let's do that now. Construct a test sphere. So what we're going to do is m_object list dot pushback, like so, std : make shared constructor shared pointer to qbrt : object sphere of type object, that's just object sphere like that. And we are going to construct a qbrt : object sphere object, like so, with the default parameters. So that what that will do is create a new instance of our sphere class from the previous episode. We'll then construct a shared pointer to that using this syntax here, and we'll then push that back into mObjectList. Okay, so that's everything we need to do there for the moment. The other thing that we need to do is here where we test for intersections. Now, of course, because we now support multiple objects in principle, although of course at the moment we still have just one, we need to modify the actual code that deals with testing for intersections. So rather than simply testing whether we have valid intersections like that, what we are going to do is we are going to test for intersections with all objects in the scene, just like that. Okay, so we're going to do for auto current object in m_object_list, like that. So that's going to loop through all of the objects in object list, giving us a reference to each one in turn in current object. And here we're actually now going to do our test intersections, which is going to be very similar to this code here, except, so in fact what I can do, I'm going to copy that bit of code from there, and we're going to do bool valid intersection is equal to current object test intersection, like that. That's the big difference, okay? And then really after that, everything else remains exactly the same. So what we can do, let's just copy that bit of code out of there and paste it in there, and then we're just going to need to tidy that up. So just rearranging the code really that we wrote previously, like so. Okay, so now we're looping through all of the objects. For every object in our scene, we test if we have an intersection or not. If we have an intersection, we compute the distance between the camera and that point of intersection, and then we're setting the pixels to red exactly as we did before. So that's not tremendously exciting, but we are going to save that, and we're going to compile it and run it and just make sure that everything still works as it should. So let's go to our terminal. So here we go at my terminal. Go back into the main folder. Run make clean. Yeah, everything is fine. Run make to compile. Okay. Scene.cpp line 37. Let's have a look at that. Oh, that should be right. Okay. Save. Back to our terminal. Make m_testsphere is not defined, of course, and that is, of course, because I forgot to delete the old code here. My fault. So let's delete that. Like so, and save. Back to our terminal. Make. Okay, and now we should be able to run that. And indeed we can. However, notice that our red sphere is now mysteriously blue. And this is a really interesting bug that has cropped up simply because I've changed my computer system since I made the last video. It has to do with whether we're using big endian encoding or little endian encoding, actually. So let's have a look at the code for that. So to fix this, we need to look in the qbimage.cpp file. And we need to just go down to the bottom where we have this function here to convert colors. So the purpose of this function is to take our individual double precision floating point values for the red, green and blue channels and convert them into single uint32 values that we can pass to SDL2 to actually create the image. And the problem that we have now is because of this difference between big endian and little endian encoding. Rather interestingly, when I've changed my computer system, the version that it's using has changed. So this is the code that used to run before, meaning that my previous computer system obviously used big endian encoding, whereas now we're using this code, which is little endian encoding. However, the R and the B are the wrong way around, so we simply need to change R to B and B to R, and obviously G for green stays where it is. So if we save that, go back to our terminal, run make again, and /QBarray, we now get the red sphere that we had originally, which is obviously a big relief. Okay, so what we want to do next is have a look at how we can actually go about implementing lights. So to store our lights, we're going to use a base class exactly in the same way as we did for objects. And again, we're doing this so that we can have multiple types of light that we can store all in one single list, which is obviously very convenient. So I've gone ahead and created a new file called lightbase.hpp, and as always for our header files, we're going to do ifndef lightbase h, then we do #define lightbase h like so, #endif, just like that. Include guards, very important, I've spoken about them before. We need to include a bunch of stuff. We need to bring in memory, and we're going to need to bring in /qblinalg/qbvector.h, like so. We have to bring in array.hpp, and we need to bring in objectbase.hpp. Okay, and as always, we're going to put this into the qbrt namespace, like so, and we're going to define our class called class lightbase, just like that. And we have, of course, our public member functions for this. We have the constructor and destructor. Okay, so the constructor, simply that. And we have to declare the destructor as virtual because it needs to be inherited by anything that inherits from this base class. And now we have the function to compute illumination contribution. Okay, just like so. So this is going to be virtual, of course, because we want to override it. So virtual bool compute illumination const. So this is going to accept a QB vector of type double, like so, reference intersection point, and a const QB vector of type double, reference local normal. So those are the point of intersection in our 3D space and the normal of the object at that point, respectively. I always like to tab my code out like that. You don't have to do that, I just think it looks rather nice if you do. We then have const std vector of std shared ptr of type qbrt : object base, like so, a reference object list. Now, for reasons that are not going to be obvious from this episode today, the compute illumination function in the classes for the lights will need to have a reference to all of the objects in the scene. It's going to use that when it comes to calculating shadows, but we're going to talk about that in another episode. We also need a reference to the shared PTR of type qbrt : object base, reference current object. Okay. Again, we'll talk about that in another episode. And then we have QB vector double, not a const this one because it's a return, reference to color, and double reference intensity. Okay, that's it for the function declarations. We then also have a couple of member variables that we need to store, because we need to store the color of our light, like so. And we need to store its location, underscore location. Those are both three-dimensional vectors, and of course we need to store its intensity, and save that. There we go. That is everything that we need for lightbase.hpp. So let's move on to having a look at lightbase.cpp. Okay, so I've gone ahead and created the file lightbase.cpp. And in there we need to include just lightbase.hpp that we've just defined. We then need to, of course, define our constructor as qbrt : lightbase : lightbase, like that. It doesn't actually need to do anything. And we need to put in a definition of the destructor as well. Tilde lightbase. So again, that doesn't actually do anything. And we need to define the function to compute illumination, which is bool qbrt : lightbase : compute illumination. And as before, we have const qb vector double, like so, reference int point, and const qb vector double reference local normal. and I'm tabbing things out to keep them nice. Const std vector of type std shared ptr of type qbrt : object base, reference object list, and const std shared ptr type qbrt : object base, reference current object, like so, and our return variables, which are qb vector of type double reference color and double reference intensity, just like that. And we don't need a semicolon because we are declaring the function. We don't need to do anything, but this function is designed to return a boolean, so we simply return false. That is the default operation of the function, and that is indeed absolutely everything that we need in lightbase.cpp. So let's have a look at how we would actually implement a point light, a very basic point light. And to do that, we're going to create a new file called pointlight.hpp. Okay, so I'm in my file pointlight.hpp, and it's going to need include guards as before. Pointlight h, hash define pointlight h hash endif, like so. And we only need to include one thing. We just need to bring in lightbase.hpp. We don't need anything else. We're going to put everything into the qbrt namespace, as we're doing with everything else, and we declare our class pointlight that inherits from public lightbase, just like so. And we have our public member functions. We have the default constructor. Okay. Oops. Light, like so. We need to override the default destructor. Okay, that's compulsory for any class that inherits from lightbase. Virtual till point light override, just like so. And we of course need to override the function to compute illumination. Virtual bool compute illumination const qb vector double reference int point const qb vector double reference local normal const std vector type std shared ptr type qbrt : object base reference object list, and const std shared ptr qbrt object base reference current object, and of course qb vector type double reference color and double reference intensity. And not forgetting the override keyword because we're overriding that. Okay, that is everything for pointlight.hpp. Really, we don't need to do very much. We only have the one function for a very basic point light. So let's have a look at pointlight.cpp, how we would actually implement this. Okay, so I've gone ahead and created my function pointlight.cpp. The only thing we need to include here is, of course, pointlight.hpp that we've just defined. And we're going to define our default constructor first, of course. It's qbrt : pointlight : pointlight, like so. Now we are actually going to put some code in here. I want to declare a default color, which is going to be qb vector type double, initialized with std vector type double 1.0, 1.0, 1.0. So that will set up our default color to white. We have n intensity. The default intensity is equal to 1. Now we don't need to worry about setting a default location because the qb vector class will take care of that for us. The default location is going to be 0, 0, 0, or the origin, which is perfectly acceptable. We need to define the destructor, even though we don't actually use it, but we need to do that. Point light, : till point light. Okay, and of course we need our function to compute illumination. And this would be the last time that we have to type out this rather long function declaration. qbrt : point light : compute illumination const qb vector double reference point const qb vector double reference local normal comma const std vector std shared ptr qbrt colon object base reference to object list and const std shared ptr qbrt colon object base reference current object and qb vector double reference color and double reference intensity. Okay. So in here we are actually now going to put in the code that will implement the maths that we were looking at the beginning of the video. So the first thing that we need to do is we're going to construct a vector pointing from the intersection point to the light. Okay, that's pretty easy. It's qb vector double light dir is equal to m underscore location, that's the location of our light, minus int point dot normalized. Just like that. Okay, so that calculates the vector between those 2 points and then normalizes it. We're only interested in the direction, so it's essentially a unit vector pointing in that direction. We're then I'm going to put this in, compute a starting point. Now, we're not going to do anything clever here at the moment, but when we come to look at other things, this will be much more important. So for now, we're simply going to do qb vector double start point is equal to int point, okay? Which makes no sense. There's absolutely no reason to do that at all. We're wasting memory essentially, but bear with me because when we come to look at later episodes and we implement different shapes, that will be much more useful. Okay. We're now going to compute the angle between the local normal and the light ray. Okay, so we saw how we could do that. Now, there's an important point here. Note that we assume that local normal is a unit vector. That's really important because we know light dir is a unit vector because we defined it to be that way, and we're going to assume that local normal is also a unit vector. Now the good thing about unit vectors is they have a magnitude of 1, and if you remember to the equation that we saw before, we take the dot product of the two vectors divided by the product of the norm of the two vectors. So if the norm of the two vectors is 1, as it will be for a unit vector, then it's 1 times 1, which is 1, so we don't need to worry about the denominator of the fraction, which is very convenient. So we do double angle is equal to arc cosine, the inverse cosine of qb vector double, like that, colon dot, because we want the dot product function of local normal and light dir. And that's it. That gives us our angle. And, okay, so if the normal is pointing away from the light, then we have no illumination. Okay, so if angle greater than 1.5708, which is approximately pi by 2, so we know in this case we have no illumination at all, right? So simply do color is equal to m color. It doesn't actually matter, but we return the color anyway. Intensity is equal to 0.0, and we return false, okay, because we didn't do anything else. So in this case, we do have illumination, right? So we need color is equal to m color. Obviously, that's the same. And now we compute the intensity. So we have intensity is equal to the default intensity of the light, so that we've stored, it can be any number, okay, multiplied by 1.0 minus angle divided by pi by 2, or 1.5708, semicolon, and return true, because we did have illumination, okay. This is the equation that really does everything, and you see what I mean about the intensity is linearly proportional to the angle between the normal of the surface and the direction of the light. So we simply basically normalize the angle. So and do 1 minus that. So that's going to, at 1.5708, that's going to be equal to 1. So that will give 1 minus 1. The intensity multiplied by 1 minus 1 is intensity multiplied by 0, which of course gives 0. So that's the point at which it will be darker. And then if it's greater than that, we have this code that just forces the intensity to be 0 anyway. And if the angle is less than 1.5708, less than pi by 2, then we're going to get some relevant fraction of that accordingly. Okay, so that's it for pointlight.cpp and pointlight.hpp. So what we need to do now, because they still won't actually do anything, we need to go back to our scene.hpp and scene.cpp files, and we just need to make some minor changes there. So let's look at that now. Okay, so I've jumped back into scene.hpp, and what we need to do, we need to hash include our pointlight.hpp that we've just defined, like so. And we need to store a list. Here we're going to create list of lights in the scene, and this has a very similar syntax to what we've used for objects. So we do std vector, std shared, ptr, qbrt : light base, m light list, just like that. Okay, that is everything that we need to do in scene.hpp. So let's have a look at scene.cpp. So I'm here in scene.cpp, where we construct a test sphere, and we demonstrated how that worked. So what we need to do is, in the constructor for scene, we are going to construct a test light. We're going to create just a single light source. At the moment, we're not worrying about multiple light sources. There are some complexities to multiple light sources because of handling how they all contribute to the color at a particular point, but we'll come to that in a later video. What we're going to do here is do m_lightlist dot push back, like so, and we're going to push back std make shared qbrt : point light, make a shared pointer to our point light, and we're going to push back qbrt point light, like so. So that will call the default constructor on from our point light class. So that's going to set that up. And what we're going to do, we don't want it at the location that is, so we're going to just modify mLightList at 0. Like so, dot at 0, because we know it's the first one. mLocation, like so, is equal to qb vector double initialized with std vector double, and we're going to put this at x is equal to +5, y is equal to -10, and z is equal to -5.0. Note that z is negative. I'm going to talk about that in a moment. Okay, so that's the location, and mLightList.at0. I'm going to change its color. Its color is actually already defined as white, but I want to modify, just for the way that we've done things at the moment, I want to change the values. std vector double, and put those to 255, like so. And save. Okay, so that's all of the changes we need in the constructor. That's going to create an instance of our pointLight class and put it into m_lightlist, and we're then going to modify its location and its color according to these values here. So if we look back to the render function, okay, so we've already modified this at the beginning of this video to handle multiple objects. What we need to do now is put in the code that we need to deal with light sources. So obviously we only need to worry about doing anything with light sources if we have a valid intersection. So this code is going to go in here inside the if valid int block that we have there. Now the first thing we're going to do is compute intensity of illumination. Okay, so to do that we create some variables, double intensity, qb vector type double color 3, like so. Bool valid illumination, which we initialize to false. And then we're going to loop through all of the lights in our scene. So we have for auto current light in m_light list, just like that. Okay. Now we need to work out, do we actually have valid illumination or not? So we do, for this light, so we do valid illum, like so, is equal to current light, like so, compute illumination, and we're going to pass to this our intersection point, okay, and our local normal. Notice those come from here, so when we call the test intersection function on the current object, it returns the intersection point and the local normal, and then we're passing those to the compute illumination function for this particular light source. We pass m underscore object list, current object, okay, so object list, that's obviously our list of objects. Current object is from here, this is the current object we're dealing with. As I say, those are not used at the moment, but you will see in later episodes why we need them. Current object, and we pass color and intensity that we have just defined. Okay, so for the moment this code is hard-coded to only really cope with one single light source. Even though I've put in a loop and everything, we're going to need that later. For now, we're not going to worry about that. What we are going to do is just down here, this is the old code we had to compute the pixel color, and we set it to some variant of red depending on distance with the camera. Now I'm going to modify this code here so that if we have valid illumination, so if valid illum is true, then we're going to do output image dot set pixel x, y, and we're going to set the red channel to 255.0 multiplied by intensity. So that's intensity that we've picked up from here, which has simply been returned by the compute illumination function. And we're only going to modify the red channel, so we set the others to 0 like that. You missed a bit, and we need an else here as well. So if we don't have valid illumination, we make sure that we set the pixel x, y to black. Okay. Okay, and that should be everything. Okay, so we save that. Let's go to our terminal window and let's see if this will compile without any errors. Make. No. Okay. Lightbase.hpp line 28 qb vector c. Yes, I've missed out the capital V. So let's go to lightbase.hpp, and it will be, I suspect, here. That's std vector qb vector. There it is. Okay, and save. Okay, let's try again. Okay, and let's run /qbarray. And that's not good. Okay, let's just do make clean. I do find it useful sometimes to run make clean just to clear everything up after we've made changes to, particularly to like data storage and stuff. Let's see if that fixes that problem. /qbarray. Okay. Okay, so we get the right distances, but we're not getting any image. So let's have a look. Why would that be? Okay, so obviously there's something wrong there. We just get a blank window. That's really not what we wanted. So I must confess it took me a bit of digging to find what the problem is, but it turns out that actually we need to make a minor change to objectsphere.cpp. So let's look at that now. Okay, so I'm in the objectsphere.cpp file. This is the file we created in the previous but one episode, actually, when we first looked at creating a simple shape. And the problem is that we don't actually compute a value for the local normal. There's nowhere in this code where we actually do it, because until now we haven't needed it. And of course, as we've seen with the theory we've been looking at, we need to know the local normal, or the normal of the object at the point that we're trying to calculate the illumination for. But at the moment it isn't returned, and luckily, because the QB vector class initializes itself properly to all zeros, local normal is always just going to be 0, which is why we don't see anything. Makes sense, right? So just down here, after we determine the intersection point, okay, we are going to put in code here to compute the local normal, which is easy for a sphere at the origin. Luckily, okay, I like things that are easy, so we do local normal is equal to the intersection point. Simply that. So the normal, because we have a sphere defined at the origin, the normal vector is simply the vector from the origin to the point of intersection, which is just the intersection point. So that's really easy. And we simply then just need to normalize that, like so, local normal dot normalize. So we save that. Now if we go back to our terminal, here we go, Now let's run make, and if we run ./cubearray, yes, there we go. We actually now get the result we wanted. We now have a red sphere that is correctly shaded according to our light source. Now, one thing I did mention at the beginning was that I did position the Z coordinate as being negative. So let's just have a look at that. If we go back to let's go back to our scene.cpp file, and here we are in scene.cpp, and I defined the position of our light there. So if we change Z to be +5, which should be up, and save that, let's go back to the terminal window. Let's run it again. ./cubearray, and now we get, you see the result is upside down. So at the moment the Z axis, the vertical axis, is inverted. That is something that we will need to look at as we go forward. We could ignore it and we could keep it the way it is, but I think it could be better to change that around. So there we go. That's really everything that I wanted to talk about today. We've had a look at how we've modified our code so that we can go on to support multiple objects. We've implemented very basic point light sources, and we've created the basic structure of code we need to be able to support multiple light sources, although we can't do that yet. And we've managed to shade the sphere that we've created at the origin according to the illumination from one point light source, which is pretty cool. So, I mean, we're not taking into account any advanced materials or, physically based rendering, PBR, or anything like that, but, it's something. We're starting to get towards something a little bit more interesting, which I think is quite exciting. So at the moment we're limited to a single sphere of unit radius positioned at the origin, and I haven't really spoken much about why that is. And I mean, obviously that's not necessarily the situation that we want to maintain. It would be much nicer if we could go on to have multiple spheres, and obviously to put them in different places and make them of different sizes. And there is a very good reason why I haven't done that as part of the sphere equation. Now obviously you can put the radius and the location of the center of the sphere into the sphere equation and calculate it that way, but that technique isn't actually generalizable across different types of shapes, so I haven't done that. What we're going to do in the next video is look at using geometric transforms to define the position of shapes instead. Okay, well, that's really everything that I wanted to talk about today, so I really hope that's been of interest. If it has, please hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss the next episode when it does come out. That should be good. And we are starting to now create something a little bit more interesting with our very simple but functional ray tracer. Anyway, listen, it's been a pleasure. I really hope you've enjoyed the video, and yeah, I really look forward to seeing you in the next one. Thank you very much for watching. Bye.